In this video, I'm going to present a rather technical derivation of an important equation of quantum theory, the continuity equation for probability, which both relies on the Born interpretation of quantum theory and also serves as a sort of sanity check for it, because it establishes the conservation of probability. The idea here is that even though we cannot say with certainty where exactly our quantum particle is located, we can be sure that it's located somewhere in space. So if we perform a measurement and look for the particle everywhere, we're going to find it with a probability equal to 1. And this total probability never becomes smaller than 1. It certainly cannot become larger than 1. So it is conserved. And this simple conservation law gives rise to this continuity equation that we're going to derive. Now, the form of this equation is actually not specific to quantum theory, and it appears in many different fields of physics. So rho here is the density of a conserved quantity. In our case, this is the probability density, which per the Born rule is equal to the absolute value of the wave function squared. And J here is the probability current, which we actually are going to derive. So to see that this equation indeed describes some sort of a conservation law, let me consider an arbitrary volume in space. So let's say this is a volume V. And let me also denote the surface encircling this volume as dV. And let me be interested in the probability of finding the particle of my quantum particle inside this volume. So this probability, let me call it P sub V, is going to be an integral of the probability density, rho, which appears here, over this volume. Now, to look at the dynamics of this probability with time, let me integrate both sides of this equation over the volume. Well, the right-hand side here is 0, there is not much to integrate. But the first term is going to give me just dp over dt, and the second term is going to be an integral of the divergence of J, and everything, the sum of these two terms is equal to 0. Now, at this stage, I can use the Gauss's theorem to handle the second term, which tells me that the integral of a full divergence over a volume is equal to a flux of the vector of which I calculate the divergence through the surface surrounding my volume. So this is my dV. So in ds here is an elementary surface element with the vector pointing outwards. So I'm sure some of you have already seen the Gauss theorem, let's say in the theory of electromagnetism. But if you forgot about it or you have never seen it, so let me just mention that this Gauss theorem is in some sense similar to the simple identity that we oftentimes use for usual integrals. So let's say if we have an integral between a and b of a full derivative of a function df dx, so we can write the result as f of b minus f of a. So essentially in this case we have a one-dimensional segment from a to b over which we integrate, and if we have a full derivative we can only focus on the endpoints. So that's the only thing which enters the final result. So likewise, if we have a more complicated integral now, an integral over a three-dimensional volume but of a full derivative, which divergence is, so instead of having two boundary values, we have a surface integral going through the surface, through this dV. So in some sense, this dV is similar to A and B, so the volume is similar to the segment of between A and B, and the full derivative df over dx is similar to the divergence of G. So what we actually have established here is that the derivative, let me call it P dot, of the probability of finding a particle in the volume V is equal to minus a flux of the probability current, again we're going to derive it a little later, through the surface surrounding this volume. And let's say if we have a current, let's say, going outwards here locally, so that there is, let's say, it forms a small angle with this ds, so then this j dot ds is positive, which corresponds to a negative change in the probability. So, and it makes sense because it means that the current carries away the probability, and the probability of finding a particle inside decreases. So if we, on the other hand, have the current going inside, the probability is going to increase. So in order for me to prove the continuity equation in the form I just formulated, let me calculate directly the probability of finding my particle in the volume V over time using the Born rule. And the Born rule basically implies that I calculate the derivative of this integral of the volume of the absolute value of my wave function squared. And the absolute value can be written, of course, by definition as a product of the wave function and its complex conjugate, everything integrated over the volume. So now, if I apply this derivative to this product, I can write it as psi star dot psi plus psi star psi dot. So in order for me to simplify it further, let me just use the Schrödinger equation in its standard form, which actually appears on the logo of our course. So and express the psi dot from here as simply minus I over h bar Hamiltonian acting on psi. So I just divided it by h bar and multiplied both sides with the imaginary constant I. So I can also derive the same equation with for psi star dot, and since Hamiltonian is sort of real, it has just the kinetic and potential energy, is going to be plus I over h bar h acting on psi. Now my h here is a combination of kinetic energy and the potential energy. So kinetic energy is a sort of an involved operator, which is the momentum squared, and potential energy is just a multiplication. It just multiplies my wave function. So if I put everything together, what I will find is the following for PV dot. So I'm going to have here, instead of psi star dot, I'm going to have this guy. So I h bar h psi, and here I'm going to have minus I h bar psi star h psi. So if h were a number, so these two terms would cancel each other out, and it does happen, as a matter of fact, for the potential energy term. So if so this h can actually be replaced with the kinetic energy. But there's no cancellation necessarily for the kinetic energy, because again, this is an operator which acts on different functions here and here. And this operator is equal to just p squared over 2m, or minus h squared over 2m Laplacian, so which I write as delta nabla squared. So again, putting everything together, so what I have is minus I h bar 2m, which I can factor out outside the integral, and in the brackets I'm going to have the Laplacian nabla squared psi star times psi minus psi star nabla squared psi. So the last step here is to integrate this expression by parts, and if I do so essentially by moving this delta from here to here and from here back to here, so I see that these terms become identical and cancel each other out, and the only term which survives is the full derivative of delta psi star psi minus complex conjugate to it. So and this whole thing, well, times this coefficient, is exactly the current that we have been looking for, because again we ended up with the full derivative of a vector integrated over the volume, so we can write it as minus an integral of some j over ds over the surface sort of encircling our volume. So finally we can just collect everything from this expression and write the final expression for the current, which I will write in the following form. Is going to be 1/2 psi star p over m acting on psi plus complex conjugate. And so the reason I can write it like this is because p is an operator which is equal to minus I h bar nabla, and this minus I h bar nabla appears here. And so if we look at these final expressions, we see that, as a matter of fact, it makes sort of intuitive physical sense, because in classical physics, a classical current associated with the density ρ is simply the density times the velocity with which it moves. Now here in quantum mechanics, the momentum is an operator, and so velocity, which is momentum divided by m, is also an operator. And this operator sort of acts on the density, which is ρ is psi star psi. So so this is the final result, which connects the change in the probability of finding a particle in the volume V with the flux of a certain probability current flowing through the surface.